This is the third mini lecture for section 4.2 of the textbook. So we're going to continue our discussion of prime numbers now. Seeing how important prime numbers are, we'd like to answer some questions. First of all, how many primes are there, and can we list them all? Or if we can't list them, is there a formula or something for finding them? Second, given a large number, how do we determine whether it's prime? For example, if I had the number 1023 or 419 or something like that, if I want to figure out whether it's prime, do I really have to check all of the possible factors up to that number before I can decide, yeah, it's prime? Or is there some way of shortening the work? Okay, so the answer to the first question is that there are infinitely many primes. That was proved by the mathematician Euclid in about 300 BC. And you can read the proof of that in your textbook. So this is something that's been known for quite some time. However, it's something that people still puzzle over, because it would be nice if we knew about some kind of pattern or formula for the primes, some way to predict where they're going to occur. And we don't have anything like that. There's no formula. Once you get above a certain point, they become pretty hard to find, so they're pretty rare. The larger the numbers are, the rarer the prime numbers become. But we don't really know a whole lot more than that. So when I made this slide, unfortunately it's a bit out of date now, but when I made this slide, the largest known prime was 2 to the 77,232,917th power minus 1. So this is big power of 2 minus 1. It's a really big number, and it was discovered in 2017. Actually, they discovered a bigger one in 2018 or 2019. So I need to update this. It's important in modern computing to have large prime numbers at hand because they're used in the encryption of data. So that they serve a big role in sending encrypted data over the internet. So it's something people are definitely interested in. Okay, but how do you find these big numbers? If you have a big number that you think is prime, how do you test that? It's going to take a long time regardless, but can you shorten the work in any way? So the answer to the second question is that we can use theorems to limit the divisors that we have to check to a relatively small list. Okay, so first, notice that in the rainbow diagrams were kind of like seesaws. Okay, they balance on the square root of the number. So for example, let's go back to 60 and 36. The number 36 was itself a square number, and its square root, 6, is right in the middle. Now, 60 is not a square. It's not a perfect square. If I were to use a calculator to compute the square roots, I would get 7 point something, which is, it's here in the middle. So the square root of 60 is in that middle part of the rainbow diagram. And of course, square root of 36, that is the middle of the diagram. And this is true in general. A rainbow diagram is like a seesaw that balances on the square root of the number. And that tells me that if there's a factor that's greater than the square root, it has to be balanced by its mate that's less than the square root. So any factor greater than the square root is balanced by the factor in its pair that's less than the square root. Which means that if I've tested everything up to the square root of the number and I haven't found any factors, then the number must be prime. Because if there's no factors down here, there couldn't be any factors up here either. So for example, the number 37, its square root is 6 point something. And if I didn't know 37 was prime, I could test 2, 3, 4, 5, and 6. None of those go into 37. That means there's nothing up here that goes into 37 either. So 37 is prime. Okay, so that means that we don't have to test nearly so many primes. So if a number is not divisible by any numbers between 1 and its square root, then it must be prime. Now, if a number is divisible by a number m, then it must also be divisible by all the prime factors of m. That's an n here, that should be m. So therefore, all I really have to do is test for prime factors. If a number is divisible by a composite number, it's also divisible by the prime factors of that composite number. So if I know that no primes less than the square root of the number divide the number must be prime. So as our theorem states, if n is not divisible by any prime numbers less than or equal to the square root of n, then n is prime. So if you're wanting to decide whether a number is prime, it's handy to have a list of small primes for checking this. And a convenient way of forming such a list is called the Sieve of Eratosthenes. And I'm going to show you a process that I want you to know, but you'll maybe have to reproduce it yourself. It's the process that's important, not just the final answer. Okay, so this process we're going to go through is called the Sieve of Eratosthenes. A sieve is a tool. You often see them in sandbox toys. Looks kind of like this, where you've got a hoop of metal or plastic, like that. And at the bottom of the hoop, there's a little mesh. So that when you pour sand through there, the mesh catches all the sticks and rocks and other items that you might find in sandboxes, and it lets all the pure sand fall through. Okay, that's called a sieve. And this process, it's kind of like a sieve for numbers. You pour the numbers through, it catches the primes. Those are kind of like the sticks. And then lets all the other numbers fall through. It's named after Eratosthenes, who is a Greek mathematician who lived in ancient times and is famous mainly for having been the first person to estimate the circumference of the Earth, which he did using simple geometry. Now, let's go through the process. So the number 1, remember, it's called the unit. It is not prime or composite. So let me just color that in. Really, it shouldn't even be on the list. Okay, the number 2 has to be prime. Let me circle that. It has to be prime because it's right next to 1. It could only be divisible by itself in 1. There's no other possibilities. So 2 is prime. However, none of the other multiples of 2 are prime. So that means I need to X out all the other even numbers. So I just go through the whole chart, Xing out all the evens. And that means I'm eliminating half the numbers under consideration. So these numbers are like the sand falling through the sieve. We caught the 2, the other ones fall through. Or maybe it's the primes that fall through and we're catching these. I don't know how Eratosthenes thought about it. Okay, there we go. But you see we're already halfway done because we've eliminated half the numbers to test. Actually, we're a lot further than that, as you'll see in a moment. Okay, now, next step. And this will be the same step from here on out. We go to the next number that we have not circled or xed. We circle it, it has to be prime. In this case, it's 3. and then we x out all of its multiples. So 3 has to be prime, because otherwise it would have been x'd already. But none of its multiples are prime. So we have 9, 15, 21, 27, 33, 39, 45, 51, 57, 63, 69, 75, 81, 87, 93, and 99. Okay, now same thing. I circle the next number that hasn't been circled or x'd yet. That's 5. And I get rid of all of its multiples, which would be 25, 35, 55, 65, 85, and 95. Okay, then the number 7. I circle 7, that's prime. I x out all of its multiples. And let's see, there's 49, 77, and that's it for 7. Okay, now here's the amazing part. I've checked all the numbers up through 10 so far. Okay, so I know that I haven't missed anything less than or equal to 10. Now 10 is the square root of the largest number on the list. If there were any composite numbers left on the list, they would have to be less than 100, which would mean they would have to have a prime less than the square root of 100. So they'd have to have a prime factor among 2, 3, 5, and 7. But I've x'd out all the multiples of 2, 3, 5, and 7. So therefore, because I have x'd or circled everything up to the square root of the largest number, I am done. Everything that is not x'd yet has to be prime. So now, without doing any more checking, I can circle everything that's left. And there's a nice list of primes. These are all the primes that are less than 100. So, at the beginning it seemed like we were going to be doing this for a while. But actually, once you've x'd out all the even numbers, there's not a whole lot left to check. So there's all the primes less than 100. So the point of doing this is to have a list of primes to test numbers with. For example, let's decide whether 281 is prime. Okay, the square root of 281 it's 16 point something. So I'll just write 16 point something. Now use a calculator to figure that out. So I list the primes less than or equal to 16 point something. Be 2, 3, 5, 7, 11, and 13. Okay, there's 6 of them. And then I just check whether each of these goes into 281. 2 is an obvious no. 3 is no. 5 is no. 7, let's see, 7 goes into 28. So it goes into 280. So it does not go into 281. 11 goes into 220, but it doesn't go into the difference, which would be 61. That's a no. And 13 goes into 260, but it doesn't go into 21, which is the difference, so that's also no. So because none of those go into 281, 281 is prime. And that's that. Okay, so here's the homework. Remember, it's section 4.1. When you work the numbers involving primes, remember, try to use a calculator as little as possible. In particular, in number 17, try to answer by just counting using primes, like I did in the examples.